Hi, welcome to the Humans of AI interview series, where together with my guests from academia and business, we try to demystify what AI is and what it's not, hopefully making this whole concept a bit more approachable and digestible. Today, we are welcoming David Barber. David received a BA in mathematics from Cambridge University and PhD in theoretical physics from Edinburgh University. He's the director of the UCL Centre for Artificial Intelligence, which aims to develop new generation AI techniques. He has a broad research interest related to the application of probabilistic modeling and reasoning. And David is also fellow of the Alan Turing Institute and the chief scientific officer of Infer, an AI spin-out from UCL. So without further ado, welcome, David. So, hi, David. Thanks so much for finding time to speak with me.
You're welcome.
So I will start straight away by asking you, how did your journey with AI start?
A long time ago,
Mm-hmm.
I was very interested in the idea of how physical systems might be able to do computation. And actually, I was in Germany at the time, and I heard about this idea that sort of neural systems might be sort of represented by sort of simple units that are either sort of active or not, like neurons in the brain, and they're somehow connected together. And whether or not a system of such interconnected sort of artificial neurons could actually compute something interesting. Could it store patterns? Could it recognize patterns? Could it generalize to new situations that it hadn't seen before? So I thought this was a very interesting idea. And at the time, there were a lot of physicists who were interested in this idea because it actually was very connected to other areas of science, particularly in an area called statistical physics, in which people have been studying related systems, particularly magnetic systems, in which you had sort of little units which were like mini magnets. And if these mini magnets were connected in some sense to each other with certain strengths, could you understand the capabilities of that collection of little mini magnets? You know, could it, what was the capacity of that magnet? You know, how strong was it, etc. So there were a lot of calculational techniques which the physicists were employing to try to calculate those properties. You know, so you have these, if you like, microscopic descriptions, in that case, of mini magnets, or how in the neuronal sense, you know, what's the description of a neuron? How is it connected in a microscopic sense to other neurons? But what you're ultimately interested in is some macroscopic property, such as in the magnetic system, the overall magnetization of this collection of mini magnets. And in the neuronal sense, the capability of this system to store patterns and to recognize patterns. So how do you bridge that gap, you know, from the microscopic description of the system to some kind of macroscopic property? And so I was very interested in that area, and so I did a PhD in theoretical physics to try to use those calculational devices and apply them to understanding this sort of neural network type systems. So that's something that I did in the beginning, and I guess it started there really, and it's been a long journey since then. You know, a lot of ups and downs, I guess, in the field. So obviously we're in a big up at the moment, but it's, you know, it's a part of a long story, which I'm very happy to tell you more about if you're interested about the, you know, the ups and downs of the whole field. But
yeah, definitely. I really love your experience, because you come from academia and you transitioned to successfully to business. But I will ask you about that later. But so straight away, I can tell you, like, I don't have almost any clue about the Bayesian methods, but I know that they are very popular among scientists who attempt to model human cognition, right? And majority of your work, as you said, focuses on probabilistic techniques and causality. Could you talk about your findings around this? Because I know that there's a lot of applications right now which use this.
Yeah, so fundamentally, I think one of the ways to think about why probability is useful in AI is that, ultimately, imagine you have a machine that you're some kind of AI machine.
Mm-hmm.
This machine tells you some prediction, and it's like a real person. Let's imagine you have a real world colleague, and you ask them to make a prediction.
Mm-hmm.
And if that prediction is wrong, if they're very confident, so you should definitely do this, and actually they're right, that's great. But if they're wrong, then you might start to lose a little bit of trust in what that person is telling you. On the other hand, if they say, look, this is my prediction, but I'm not 100% sure. This is a certain confidence I have about the prediction. It's not great if they're wrong. They say, well, I think this is more likely than not, and if it turns out not to happen, but at least it gives you some sense of what their confidence is. If they're not fully sure about it, and it turns out that their prediction is incorrect, that's actually in some way much better than this an arrogant colleague who says you should always do
You can
this, you should
double
always do
check.
that, and
Mm-hmm.
doesn't give you actually any opportunity. Even there's no doubt in their mind about this. So actually having predictions which come with an associated confidence or uncertainty estimate about them is actually critical. That's true not just in a theoretical sense in a machine learning prediction environment, but it's actually true in business in general, and the world. The reality is the world is a very complex place. Decision making is complicated. We don't have certainty in almost everything that we do. And sometimes it's very important to have those uncertainty confidence estimates. Obviously, there are great examples in areas like finance, but weather prediction, et cetera, they all come with associated confidence estimates. And that's, I think, one of the sort of like very basic reasons why a machine which comes with an associated prediction uncertainty with it is very, very important, because otherwise, you just don't have that level. You can't build the trust that you would like to have with that machine, in the same way that a colleague which never has any doubts about what they're saying to you, pretty quickly you're going to learn to shun that colleague, because once in a while they'll get it spectacularly wrong, and you'll never understand when or they're actually likely to be accurate.
Mm-hmm, mm-hmm. So you can double check with some other source. So I know that you're working on, so as you said, like learning how to machines reason under uncertainty, and how to represent knowledge. So how do you represent knowledge?
Well, knowledge representation is a grand challenge. Actually, there's no, we've not found the single right way to do this yet. It's very, very complicated. So there's a raging, ongoing debate for many, many years about what actually is the right way to represent knowledge. So, for example, if you think about natural language processing,
Mm-hmm.
some people might say, well, you should have the text, and the machine should read some text, maybe a paragraph of text. It should extract from that representation of text a way to represent the text. So it might say, for example, a certain person is walking into a certain room, and they're picking up a certain object, and they're doing something with it. And actually, that's an extraction of that textual description, and it represents actually what's going on. What the actions are, what the objects are, etc. And that might be represented in some computer understandable form. On the other hand, some people might say, well, every time you do that, you're potentially going to lose information. You might say, well, there are subtleties in that description. The way that the person picked up the object, or the tone of voice that they're using, is not actually represented in that previous rather crude extraction and representation of the raw information that's ongoing. So other people might say you should never actually try to shoehorn this original textual description into some representation, because you're going to lose something. And so there's no easy answer to this. Sometimes it's going to be appropriate to form some representation of, for example, text. Other times you are going to potentially lose something. You might not want to do that. And so certainly situations where, if you're thinking about trying to understand what's going on, there may be some in a human readable format, and some kind of representation might be useful. But in a way, this actually goes back to almost like the heart of what AI and machine learning are really about. So if you again think about text and natural language understanding and natural language processing, this is a debate which has been going on for many, many years. So when people originally thought about how to understand, for example, written text, it seemed very natural to hire linguists, people who studied language, the structure of language, and how to represent language and sort of, what does it mean? Great examples, people like Chomsky, they would come up with structures, mathematical structures, which actually try to explain the way language works. And they're pretty, interesting, very very detailed levels and very general ways actually of representing language. And they're very, very exciting. And in a way, it's very consistent with the kind of general paradigm of reductionist science, where you try to find basic laws which explain the physical and or the what you observe. So if you're a physicist, you'll be very excited about things like Newtonian laws, Einsteinian laws, whatever there might be, very simple models, but they explain an awful lot about the way the world works. In an analogous way, you might be very excited about simple models like Chomsky's models, which might explain the way that language works, right? And these are, in some sense, like the holy grails of science, trying to find those principles which actually are replicable to, and explain an awful lot of the phenomena that we observe. Now, unfortunately, that's not that easy, particularly in areas like language. It's extremely complicated, and those rules don't really always apply that well. So, there's a very, sort of interesting examples of, and early days of machine learning and AI, people trying to do things like speech recognition. So they try to have a machine which can listen to what people are saying and then sort of transcribe that in some way and potentially answer questions about it. So it seemed very natural to hire linguists at the time, to actually help with understanding language and encode their understanding in some computer form, which would then help the computer to understand what people are saying. And so companies like IBM, who were pioneers in this, in the 1970s, they hired these teams of linguists and tried to get the system trained that way. But actually, it didn't produce particularly useful results, and the machine accuracy wasn't that great. And there was a famous story about a guy called Fred Jelinek who was leading this effort, and he said, every time that he basically tried to improve the system, and said every time he fired a linguist, the recognition accuracy improved of the overall system. So this is not, I don't want to sort of put down the linguists in this sense, but what the story really is about, that instead of using this, imposing the way we think as humans that language works in a sort of reductionist sort of way that Chomsky might have proposed. Actually, if you just look at the raw data, if you're fortunate enough to be in a situation where humans or people have labeled data, so for example, in a very sort of non-reduction space, so like this sentence means X, this word means Y, and in a very, very simplistic way, just sort of hand transcribing what these utterances actually mean in terms of a textual transcription. Then you could just try to have a machine which can learn the mapping between what you hear and what the textual transcription actually should be. So, bypassing any, what does it mean or how do you represent it? It's actually, in some sense, a very, it's an impoverished intellectually approach, right? You're just simply taking the input, which is this raw speech waveforms, and the output is some textual representation of what that person is saying, without actually any understanding actually directly what the person is saying. It's just, it's void of that. It has no real understanding of what the person is saying. But that approach, that so-called machine learning approach, which actually has a very limited understanding, doesn't really impose any a priori strong constraints on how we think the machine should understand the text, what the person is saying. but it actually just tries to use a lot of data to make up for the lack of a good understanding of how to do this. Actually, was extremely successful relatively to using a very sort of reductionist approach, where you say this is the way we think things work. This is the physical law, if you like, or the way that natural language processing should work. But rather, just say, okay, instead of that, in view of that, we'll just use a large amount of data to try to learn directly a mapping between the speech waveform and the textual output that we would like it to have. And that was extremely successful, relatively speaking. And that's journey, if you like, that approach of not imposing strong sort of paradigms as to how we think this should be done from an intellectual perspective, from a reductionist approach, has been the dominant paradigm in the last 30, 40 years. And that's been replicated across a whole range of different application areas, from speech recognition to natural language understanding to visual object recognition to robotics, etc., etc. That's really the way things have gone. Now, some people might argue, that's not the way things will end up. Eventually, it might well be that we will return to some representations and approaches which actually are have a much deeper understanding of what's going on. But that's part of really the most successful approach recently. And so in some ways it's very interesting, and it's a divergence from the classical scientific paradigm, if you like, of finding a simple set of rules which seem to be able to immediately explain the phenomenon that we observe. But actually, on the other hand, it's another way to view this is actually that, it's still, there is a reductionist principle there, but it's not quite the same as the classical paradigm. And maybe I can explain a little bit why that's the case. So if you think about maybe even, evolution, right? You could say it's in some sense, there's a process there which we can describe, and we seem to understand some things about it, in terms of genetics and how genes combine, and in a combination with their fitness to the environment, ultimately this improves, if you like, the subsequent generations of the organism. And this then evolves from something which seems in the beginning relatively simple, and it emerges at the end to be something that's very complex. Now, if you took that complicated resulting organism and you said, how does it work? How can you explain how this organism works? It's very, very difficult. It's very complicated. But if you say, can you explain what is the process by which that organism was produced or it emerged, then it could be relatively simple. There is a set of relatively simple rules. If this particular version of the organism is surviving, more often than another version, then it ultimately will be successful, and the other one will be less successful and will die out. But you can't, then sort of easily explain. You can't look at a human being, for example, and say, explain exactly how this human being works. It's extremely complicated. But can you explain the process by which this human being emerged? Humans emerge as an evolution process. Yes, that's possible. But the end product is an extremely complicated combination of these rules with the environmental factors which ended up producing this person. And that's really, in some sense, that's analogous to where machine learning goes. You can't, the rules by which we train the system, the rules of learning are clear. If this set of parameters has a better performance than that other set of parameters in terms of, say, prediction accuracy, then that's the better set of parameters. And we keep iterating, keep trying different sets of parameters until we find that set of parameters that has the best performance based upon the training data that we have and the problem that we're trying to solve. So with speech recognition, there's some, machine architecture with lots and lots of parameters to it. We know what the machine should ideally produce as an output, and we try, one set of parameters, it works okay. We modify them a little bit. We try another set of parameters, works a little bit better. Well, that second set of parameters is better. And we just iterate this process in an analogous way, if you like, to how evolution might work. And that principle is well understood. It's quite simple. But the resulting system that we get, the parameters, can we explain, the final system? How does the speech recognition system work? Can you explain it in some reductionist way? I give you the end system. How does it work? It's extremely difficult. I just can't tell you. In the same way that if you ask me, how does a human being do speech recognition? Tell me now. Here's a human being. Have a look at them. Explain how that human being was almost impossible, right? But in the same way, the kind of description, or you could argue that the way that the science works, it makes less sense. That the question is no longer the right question. It's not the question. Is how does the current system, as you perceive it, how does that function? Is maybe not quite the right question. The question is more rather what are the rules which explain how such a system can emerge when you combine it with data, when you combine it with an environment, and how does that work? And that's really what machine learning is. It's that principle, that approach, but applied to the creation of artificial systems which do data processing in combination with a lot of data.
Yeah, and that's really much relates to the ethical AI, right? Like understanding how did you arrive to this outcome. So my next question, actually, you pretty much answered, but I will read it anyway in case you want to add anything. So in your last blog post from 2018, good luck with blogging, you wrote machine learning models are still largely superficial. The models don't really understand the meaning of sentences they are translating. If we want increasingly intelligent machines, it's important that models begin to incorporate more knowledge of the world. So what do you see has changed in those last 2 years in NLP and AI in general? And how close are we to intelligent machines? And another one which I've been hearing all the time is recently, it's the GTP3 model. Is it? Yeah. So how do you see it helping into arriving into intelligent machines?
Well, there's a lot of questions there. Maybe I can just, they're all very interesting, but maybe I can just give a couple of viewpoints about it before I try to answer some of them. I think, so personally, I'm not really a big fan of the trying to, categorize things as intelligent or not. I think I understand maybe why people are excited about that, and it seems interesting, and philosophically maybe it's kind of fascinating topic, but I don't honestly think it's that practically relevant. And for the reason related a little bit to what I was saying before, people seem to accept that humans or other higher so-called organisms are intelligent in some way. But the process by which that emerged, that organism, it doesn't matter. It's not asking itself, oh, am I intelligent, or is not got some. All that happened was that organism emerged because whatever modifications it had in its behavior, they turned out to be useful for, at that moment in time, that particular way of operating had greater utility than its predecessor. And that's what it's all about. And in the same way, in machine learning and AI, all we are about is making systems which have utility. People find them useful in some way. The question as to whether or not they're intelligent or not is a philosophical issue, which I think it is interesting, but you can talk about whether or not machines are intelligent or not, and until the cows come home. And people have been talking about it for at least 50, 60, 70 years. Does it matter? Is philosophically interesting? But if you want to have a system, all of the things we do now, the conversation we're having now, is not because of 60 years of philosophy about whether or not machines can ever be intelligent, but because of the practical reality, the thing that you're using now, uses compression, which has come through engineering approaches, video compression, text compression, speech recognition. Your phone is full of algorithms which use AI and machine learning. These approaches are impacting your daily life and mine as well. That's why we're here now having these conversations. It's about the practical utility of these approaches. And in exactly the same way, the reason you and me are even here now as creatures is because there was a process which turned out to be useful, which created us to sustain our existence in this physical environment. And it seems like a very strange question to ask. Well, an amoeba, was that an intelligent organism? It doesn't matter. It's irrelevant. The process was there to construct a more surviving organism. And in a similar way, the only thing that really matters in some sense, in a practical sense for us, is, well, look, if machine learners and AI folks can't come up with anything which is of practical utility, then it's fine. But it's just a philosophical it's a party game somewhere, which is interesting, but so what? That's not the point for me. The point is, and I understand, like I said, I think why people are excited about it. It is an interesting philosophical question, but I think the more interesting philosophical questions are related to issues of ethics, because that's where there are the overlap between the practicalities of machine learning actually come up against some really hard, difficult, and important questions about how to apply these techniques in reality. But I'm less excited about questions as to whether or not this machine is intelligent. I think it's not an irrelevance in the grand scheme of things, but it's not something that I'm particularly personally excited about. And I don't think it really is that useful as a debate for the machine learning community. So having said all that, the thing that I wrote in the blog post is really, at that time, and it's still ongoing. So what I mentioned before, and one of the things I was saying, is that actually what people have been doing is we've been throwing a lot of data at systems, and we've not been introducing very much sort of constraints about how the machines should solve problems. Now, if you think about things like, say, translation, so if I give you text in English and I would like to make a version of that into Russian, for example, then there are very interesting tools which can try to do that. Now, typically the way that they work is the machine is not, say, taking that paragraph or that sentence of text in English, reading it, understanding what is going on, what the objects are, who's doing what, and then taking that understanding and translating it into Russian. It's not doing that at all. It's simply taking that text, and it's got lots of examples of how that text or similar piece of text might get translated into Russian. It's doing some kind of pattern matching, and it's making a Russian version of that. So a very simplistic approach would be to take each individual word in the English sentence, and there might be 3 or 4 correlate possible words in, say, the Russian language, and then you'd have a lot of possibilities as to what these Russian sentence translations might look like, and some of them will be sensible in terms of the grammatical ordering, in the sense that maybe statistically, if you have this particular ordering, well, we've never seen an ordering like that in reality ever, so that probably is not the right one. But that particular ordering is actually the kind of thing that we often see in Russian. Therefore, maybe that's decent translation. But that approach doesn't require the machine to understand or comprehend in any way actually what that original English sentence is saying. And this approach actually can be surprisingly good. So as far as I'm aware, this is pretty much the approach that you'll see whenever you go into some automatic translation tool. Most of them are actually doing that. They are devoid of any deeper understanding of actually what that original text is trying to say. So that's fine, but ultimately you might say this is not really quite enough. You'd like to get a sense that actually, if I was to ask you to translate a novel, that's not really the right approach. You'd really like to get a deeper understanding of what's going on, and then use that to make a suitable translation. If you're looking for consistency, coherency across the whole novel, translating things on a, in a sort of blind way, sentence by sentence, is not really going to get you that level of depth, or, that you need of understanding to actually make a consistent, coherent understanding of the whole story. And in a similar way, if you're thinking about situations where you might have, say, you might like to understand new medical knowledge, and you might have, thousands of academic science papers out there in the medical domain, how do you mine them and try to extract from them a coherent story as to what's going on, some understanding of an underlying process? And that's not necessarily, just as simple as taking a very superficial level understanding of the text. And also, in a similar way, you could argue that if you have, robots interacting in the physical world, you would like them to get some understanding of their physical environment to be able to interact more meaningfully with us. Also, if you start to talk to a robot, on a daily basis, it's maybe great if that robot behaves a bit like a person. It starts to construct an understanding of you. What are your likes? What's your pet's name?
Let's talk about, I have the question about emotions and the consciousness later.
Yeah.
Thanks so much. I'm just conscious of time. So, and another question, let's go back to the Bayesian networks. So Judea Pearl, one of the scientists, I'm sure you know, who contributed immensely to work on probability, says that the deep learning is limited to analyzing data, and that causation can never be derived from data alone. So you touched on that a lot, but he also argues that since people are able to do causal reasoning, the human mind must have some built-in machinery that allows us to create those models. So it's not only about learning from data. So do you have any, how do you see it? Do you have any other idea on that?
I'm not really I don't do a lot of research in causality, but I think I agree with Pearl largely. I think what he's, I don't want to put words in his mouth, but I suspect what he's trying to say is that in situations where you don't have any temporal information, then, how can you really be confident, or how is it even possible really to derive causality? So if I tell you, these two things, I give you, whatever it is, maybe smoking and lung cancer, for example, and then I don't tell you whether or not, the times that these events were measured, then, how could you somehow infer a causation between, say, smoking and lung cancer? I mean, theoretically, the machine has no clue what these things mean. They're just two, variables, and it doesn't, it may be very natural to humans to assume that, well, the smoking happened before the lung cancer diagnosis happened, but, the machine has no clue of that. It doesn't know that. So if you don't input, if the machine doesn't have any understanding of the temporal nature, when these events occurred, that's pretty, I think essentially it's not really, I don't think it's intellectually plausible that you can actually, really derive a causal relationship between variables. People do it, but it's not, but it actually brings in some other assumptions, things like, people look for relationships which are simplistic in some ways. So, but I agree with Pearl in the sense that I don't think it's theoretically possible to do it in the absence of temporal information. Beyond that, there's what's called interventionalism. So, if you don't actually intervene in systems, it's also quite difficult to infer causality. So if you think about medicine, people do things like randomized trials, and that's actually an approach to discover causal relationships between variables. And there's a sort of, very sort of interesting ongoing debate and discussion about, even if you have temporal information, but you don't have necessarily interventional information, you don't know if this was an intervening, it was a trial and something like a randomized trial, how can you then learn causal relationships from data? And I think that's that's more likely to be possible. That's certainly more doable. But I'm not a big fan of the idea that somehow you can infer causal relationships between variables without knowing something about the temporal sequence, when things happen. I think that's really a little bit implausible, personally.
Mm-hmm. So yes, to touch on that, I know like DeepMind uses a reinforcement learning, which is based on practice of trial and error. So maybe that's a good way of like discovering those causal relationships.
Well, reinforcement learning is not really so much about causality, actually. Reinforcement learning is just a form of interaction, if you like, a little bit like trial and error, like you mentioned. But typically it's characterized by what we would call delayed reward or delayed feedback. So the sort of more normal sort of environment that you might have heard about where AI machine learning is used is that the system might make a prediction and immediately gets some information, some feedback as to how well it's doing. So, the human or somebody might say, well, that's correct, or that's incorrect. And the machine immediately then tries to change its parameters to improve the performance in some way. But there are other approaches or other applications where that feedback is not so immediate. So if you think about game playing, for example, like you're playing chess, the machine sees the state of the board right now. It makes a suggestion for what the best move might be right now. And do you get feedback immediately? No. The only meaningful feedback is at the end of the process where you either win or you lose the game. And the challenge then in reinforcement learning is you get this delayed feedback. You don't get an immediate reward. And you need to somehow figure out, assign why was it that this particular move that I made ended up in resulting in me winning or losing the game, bearing in mind that I'm part of a competitive process in which the environment is maybe being an adversary. It's not, it's trying to, there's some other actors and operators in this environment which are also using the actions that my machine comes up with to try to figure out how to beat me. So it's a complicated process, is then how to figure out how to change the parameters such that at the end of a process, potentially a very complicated one like game playing like chess, how do you then adjust the parameters such that eventually you will learn parameters which will improve your chance to win the game. So reinforcement learning is more about that. And you could argue actually that, so some people say it's kind of the mother problem of AI. Some people really like reinforcement learning because in some sense it's a very pure problem, and they would perhaps even sort of make an analogy with evolution in the sense, that's how did those rules for genetic combination emerge. It's not a fully random system. Those the way that things combine is there are rules around that, and those rules themselves are learned by the ultimate efficacy of those rules. If you have certain kinds of mutations, or you have certain kinds of genetic combination, well, some will be more or less successful at resulting in organisms which are going to survive. And in a similar way, that process is a long delayed feedback. That immediate offspring, or that it doesn't necessarily you don't see whether or not the result of this, that organism has to grow for 30 odd years and try to survive as an environment, and eventually it may or may not survive longer than other organisms. But that is a very complicated interaction between that organism's growth and the environment, which is potentially adversarial and competitive. And how does that work? In a similar way to reinforcement learning, the feedback is extremely delayed. And the question is, how do you figure out what the mutations or the genetic processes might be such that you have a good chance of resulting in a gene pool which actually has a good chance of survival. And similarly, analogously, in say game playing, how do you figure out what the rules should be such that at the end of the game you have a good chance of winning? So people like this because they think, they feel that this is kind of like the mother challenge, if you like, around AI. And how do you associate current behavior with long-term success in a potentially very complex and even in an adversarial environment? So that's very difficult, but that's kind of the challenge around reinforcement learning. So yeah, that's the analogy, if you like.
Thanks so much for such a lengthy and interesting answer. So I know that you just mentioned that the causality, it's not your field, but do you believe that this is like critical to achieving what we call the strong AI or the artificial general intelligence, or there are some other
yeah, I mean, to be honest, I'm less keen. I don't really like the phrase AGI, and I don't think it's. I mean, I refer to my previous answer. I think it's irrelevant, and I think it's a distraction. And I think I understand why people are excited about talking about things like artificial general intelligence and all this stuff. It's not, in my opinion, practically it doesn't matter. It's a interesting philosophical discussion, but it has no bearing in the same way that an amoeba never asked itself, well, how do I get to AGI, or how to become? It doesn't make it's largely irrelevant. The only thing that really matters is making systems which have practical utility, and whether or not people find them useful and they are consistent with our ethical setup, and are they useful for society in a general sense, and also in an individual sense. So I don't really like to get into discussions about what does intelligence mean. Will we get to AGI? It's fun for marketing purposes, and I know the general public seems very excited about this. But as a scientist, I don't think it's the right question.
Yes, but you mentioned like in the example of the robots interacting with the humans, you mentioned that the area of maybe like learning about the environment and and responding in the emotional way or like conscious way, it's increasing, like very important, right? So where do you think that this is heading? Like, how do you think we can achieve models or like machines which will be responding to us, understanding the environment?
Yeah, I think we're still in in the early days, relatively, of AI. It's very complicated. I think trying to understand how humans work and how our physical world works, it's very, very complicated. I mean, even us humans, we arguably spend a good 16, 17 years before we become arguably useful members of society, right? It's a long process, and we have a head start from the way that we're designed. So machines have a long way. They've got a long way to go to catch up, just to have to get the raw information that they need to understand our physical world and our cultural world. So that's a long way to go. And getting that information, into the computer in some way, representing that, we don't really know how to do that. But what we have found is that a very, perhaps intellectually unsatisfactory, but just a pure data-driven approach actually is being pretty successful. But you could argue, going forwards, so I think right now we're still in this process, this part of the overall process where the machines are still, getting up to speed. They're still starting to get an understanding of the structural landscape about the way our world works. I think once we've got to that point, then there is a second, and perhaps a very interesting point about, well, how do you then start to feel confident that the machine really starts to understand more about us or what you're saying, or your emotional sort of feelings about what you're saying, etc. And how do these how do we feel more that we can communicate in a more natural way with machines? That's, I think, very, very important. So in a similar way, like if I wanted to be able to interact with the machine, I'd like it to be able to explain to me back why it say gave that prediction. Why did they make that recommendation? Why should I go and see the doctor? Or why should I potentially change my bank because the machine's figured out, well, maybe there's better interest rates in another bank, and etc. But I need some sense of confidence or communication capability with machine. It's not useless to have a machine that just says, do this, do that. But I think as we go forward and we want in society, we want to be able to get more utility out of machines and feel we can, trust them better. And I think having them, that they appear to give us a sense of, an understanding as to, in our human terms, as to why they took those decisions, and be able to explain that to us. I think that's very reassuring. Mm-hmm. And situations again, where if they're not confident about that and say, well, actually, I don't, this is my recommendation, but I'm not really sure because there are uncertainties here and there. I think that's very, very, very important. And I think that's where, we will probably end up eventually. But I think right now, we're still making huge progress in terms of, just getting that basic information. So you mentioned before some of the, the natural language processing models like GPT-3, which again, in an intellectual sense, they might seem very disappointing because all that they're doing is taking enormous amounts of data off the internet, and they're just trying to learn models which can predict the next word, given this current, say, whatever, past few words in a sentence, can you predict what the next word in the sentence might be? And that's it, pretty much. It's a very simplistic idea. But if there's so much data out there and so much, and these systems are enormous, the number of parameters is unbelievable, like the billions and billions of parameters in these models. But given the huge amount of data, there are statistical regularities there which can be identified, which actually can be quite predictive of what's going to happen. The world is not random. The way language works is not random. The way text works on the internet is by no means random. There is structure there to be found. But we ultimately need to exploit those understandings, I think, to be able to marry them with how to explain back to us and to gain confidence about the way that the world works. So that's a philosophical story, if you like, but there's great practical utility still in just getting machines which actually, even if they don't have that greater depth of understanding that we would ultimately like them to have, but they're still very, very useful. You can still go into a translation system, get a translation. It's great. It's very, 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 very handy to have that. And you might say, well, it's a little bit disappointing, but it doesn't have that really deep intellectual understanding of what I'm trying to say. And ultimately, we would like it to have that. We'd love to get that. There are good, important reasons why we want to get there. But still, it's still practically useful. So I don't want to, be too harsh on, I think, where we are right now in machine learning. I think we've made enormous progress, and I think that's important to focus on. It's important to recognize that all of the progress, or a great amount of the progress that we've made right now, is not through because of some philosophical debate about what AGI means, how to get there. It's because of simply a lot of hard work from engineers combining with a large amount of data that has given you and me these amazing tools where we are right now. The progress has been extreme, and it's a combination of a huge amount of data, enormous improvements in compute power. Just maybe to give you some understanding of, maybe another couple of interesting stories which are not necessarily directly mine, but if you look at the amount of compute power that's used right now, say to do speech recognition, or maybe image recognition is a better example. Basically, the systems that we use now to do object recognition are not that different to those systems that we used in the 1980s, they're basically the same. There's really no, fundamental difference. So if I showed you a state-of-the-art image recognition system, object recognition system to a researcher from the 1980s, they, oh yeah, I know what that is. That's just a example of something well known. But you ask them to train it, right? So if I take, say, whatever, 2 weeks on a GPU now, that corresponds to a certain amount of computation. And that's what's required to train that image recognition system. And I go back to that researcher from, the 1980s and say, please train this system now on your state-of-the-art machine back in the 1980s. How long do you think it would take them to train that? So what's 2 weeks worth of compute power now equal to in terms of, how long it would take in terms of, say, that 1980s person to train that same system?
Many years.
Years, right? A lot more, right?
Mm-hmm.
The answer is 250,000 years. Right? It's much, much, much longer than most people would imagine, right? Then this is the sort of almost the incredible thing about compute power. People seem disappointed that every year you only get this machine which is 1.5, maybe 2 times faster than the previous year if you're lucky. But this compounds, over 20, 30 years, you get an enormous increase in compute power, to the point we are now arguably not that far off just the raw power that you would need to do visual processing, maybe at the level that the human brain can do that. So that's it's really, really important to bear that in mind. On the other hand, so that's one great story, and another great story which I've heard and I like very much is the idea of robotics. So if you think about playing chess, you might say, well, imagine you're playing a physical robot sitting opposite you on the chessboard, and the robot's picking up the pieces, moving them, and putting them down and playing the game very well. So what's more difficult? Is it knowing what move to make in terms of what's more difficult, or just picking up the piece and moving it on the chessboard? So actually, since 1997, we've had machines which can trounce the world champion at chess. It's easy, relatively. It's an easy problem playing chess. But we still don't have a machine, a robot, physical robot that can pick up chess pieces and move them effortlessly around the chessboard. It's extremely difficult. Why is that? Because the rules of chess are a closed, simple system which we can play with in a synthetic world, and in order to figure out how to play chess very, very well, certainly compared to a human player. But the physical world is an open thing. We don't have perfect models of the way the physical world works. There are certain imperfections in the way the robot is constructed and operates, and the way the physical world works. Our perception of the physical world isn't perfect. How do you cope with all these imperfections and the reality of the world? It's much, much more complicated, and that's why people are, if you like, continually surprised why we don't have these machines running around our houses, that people have predicted for 50, 60 years. It's much, much more complicated than you might imagine. So that understanding as to how to operate with the physical world is very challenging, but it's critical if we actually want to move to robots who can actually help us in our physical environment. That's extremely difficult, but also one of the most exciting challenges around AI, in my opinion.
Amazing, thanks. I know that you have to go in 12 minutes, so let's try to touch on those. Work outside your academia, it's incredibly interesting. And I know that you are also working in House of Lords Artificial Intelligence Select Committee. It happened that my last interview was with Lord Tim Clement, so I don't know if you're working with him, but what does your work involve there, and how do you contribute to?
Well, I was involved in the one of the select committees inquiries into AI, and I think the House of Lords had a very, very good committee there. I was extremely impressed with them, actually. So, and I was a little bit naive about the function of the House of Lords before then, and
yes.
I didn't know a great deal about it, but I was invited to help, and I gave evidence at one of their committees about AI. And I was very impressed with them. I think the House of Lords perhaps compared to the members of, the standard members of parliament, and actually have a lot more time to examine, and reflect upon these topics, which actually really have potentially very profound impacts and influences on our society. And I think they've done a great job actually in producing a report which makes very sensible recommendations, I think, to Parliament and members of society about the issues that we are facing. And so I just played a very small role in that, giving my view as to a very small part of a very complicated but a fascinating picture of the interface really between how these technologies might be impacting our everyday lives, and what does it mean for us, what can we do about it. So that it ranges both from the ethical and societal, but also to the economic, and where does, for example, the UK fit in this global picture. What can we offer, and what are the unique characteristics that we might be able to exploit in the UK and take benefit from compared to, say, some other countries. So Tim did I think a great job in chairing that committee.
Congratulations. It is said that there is a huge difference between working in academia and working in the actual industry, or creating commercially viable products. And I know that you are successful, like living example, that it's possible to move from academia, or like being academia, and create something commercially successful. You are a serial entrepreneur, having founded 2 or maybe more. I just saw 2 companies, Infer, the spin-off from the university, and Optimal AI. I guess that's why you were giving so many examples in the medical sphere, right? So how did you make this transition from the academia to business? And for those who are in academia trying to do this, what would you say it's the key element to make it successful?
The reason I was interested is I think that there's, as an academic, there's we're not just interested only in the the purely academic intellectual challenges. I think the impact of our research in the broader society is extremely relevant. And as I was saying before, for me, the machine learning is a practical area. It's not a philosophical area. It's not philosophy. AI, machine learning, is about producing, in my opinion, practical tools which can benefit ultimately society. And we can remove drudgery from people's lives. They're there to help us. They are liberators of humans from being, how to pick up boxes and stack shelves, or drive cars. This is ridiculous. So how to make technology serve humanity and improve things, the environment, healthcare. These are great opportunities for us to use these techniques. And I think it's it's important that we as academics actually help that process to translate these things which we've been studying and researching in academia actually to be benefit to society, and to show how that can go. And so I've been very fortunate to have had very great students over the years, who some of them who've had a very strong academic background, but a passion also for translating these opportunities and these understandings into business, into the business world. And I think that's very, very interesting. There's a very, it's a fascinating sort of bi-directional challenge, right? On the one hand, in academia, you come up with ideas that are perhaps, pushing the academic field forward. But when you then talk to people in industry, they've got practical realities and problems that they face. And it's, trying to find that, I think, great balance. If you can come up with something that is, a new approach that actually maybe even opens up a new business opportunity, I think that's really fascinating. So I think right now, I'm particularly excited about the idea that AI can actually create new opportunities. We can do things with AI that we simply could not do before. And I think that's really, really it's a fascinating, and I think it's an important thing to be doing as a scientist. So I been, like I said, very fortunate to have very good students who have helped to create companies and doing quite well, and I'm very proud of them. I think it's one of the most exciting things you can do. If you manage, you're lucky enough to be able to do that. It's very, very rewarding, and so I think intellectually, I think as an academic, that's certainly something that I'm very, very keen on doing. And I think universities in general, we have this. Typically, there are three strands, right? The university wants to be successful in terms of research, of course, education, naturally, but also innovation. Those are the three pillars how we serve society, and I think I feel very passionate about trying to continue to do that.
Amazing. So let's talk more about your latest project, Optima AI. So you're using AI models to optimize processes in health sector. Which areas are you mostly trying to improve?
Yeah, so healthcare is, we're starting with healthcare, but we're not necessarily going to end just with healthcare. But if you think about healthcare, there are many apparently natural applications of AI in healthcare. In diagnosis is an obvious one where you might say, well, can you take this scan? Can you, somehow then see whether or not there's a certain disease in the individual? So medical diagnosis has been a very dominant application area for AI for many years. But I think there are other areas in healthcare which are perhaps less sexy in some sense, but they're also very important. So if you think about management of healthcare, so for example, patient management, do people show up to their appointments? If they don't, then the estimates for the UK is this is costing the NHS around £1 billion a year in missed appointments. So how do you tackle those kind of things? How do you maybe predict that people may show up to their appointments, and if you think they may not, what remedial actions can you take that might improve the chance tomorrow that the person will actually show up to their appointment? How do you book? How do you make sure, first of all, you should have not made that appointment booking at that time? How do you more smartly book people? If you think about situations like coronavirus now, there's an enormous backlog of patients waiting to get appointments at hospital. How do you do that? How do you efficiently get them through the system? It's a huge problem. So I think there are a lot of interesting challenges around healthcare management, operational efficiencies. We can help them with that. And I think that a lot of this stuff it's relatively, simplistic, and it's maybe not, doesn't sound maybe that exciting from a sort of like futuristic world viewpoint, but these are, I think, simple application areas that are actually very important. And so we are very passionate about trying to help sectors like the healthcare industry to improve their operational efficiencies.
And where else do you see the application of that apart from healthcare?
But there are other things like, you might say, I may give you a couple of examples. You might say, well, can you figure out how to do predictive maintenance? So you might say, in a world where there are, thousands of devices, millions and millions of devices around the world, some of which are going to be failing. How do you, know which ones might be failing? If you're going to assign human resources to go to explore and potentially to fix devices in the physical world, can you predict which ones may be more likely to fail, in the next days or so than others, and you assign your resources accordingly. Similarly, there might be things where you might have, say, people going to holiday. How do you figure out, what the demand might be for airlines or hotels or transport or all kinds of infrastructural, demands and loadings, etc. These are, application areas where you can try to understand how humans behave. What is the way that people, what is the can you predict somehow the behavior of individuals and then sort of plan accordingly in some way. That would be one application area about management. But there are also, predictions of the way the machines behave. Could you then predict failure modes, etc.? So I think it's really optimal AI. It's really about that. It's about understanding processes and where the sort of the failure points might be, and what interventions, interactions you can make to actually then efficiently use the limited resources that you have at your disposal. And healthcare is a great example of that, but it's just, it's a starting point.
Yeah, no, but you are completely right. Like the least sexy areas are potentially having the biggest impact, right? So
Yeah.
Amazing that you are tackling that. And I want to finish by asking you some of the things that we should worry about when it comes to progress on AI. Is there anything, or I don't want to go into intelligence bit because you already clearly stated what you think about it, but is there anything we should be concerned about?
I think it's important that we all keep an eye on what these technologies are doing. So I think it's for me, I want to present a very positive image of AI. I think there's a very negative viewpoint, particularly in the West, about AI. And I want people to, recognize that there are many potential upsides of AI. For example, the idea of self-driving cars is amazing. There are thousands of people in the UK every year still dying on the roads needlessly in car accidents. It's ridiculous. Yes, and the possibilities for example, automation there are amazing. There may be, a small number of accidents and potentially deaths that could arise from the application of, say, automation in, say, the automotive industry. But, that's relatively small compared to the existing, issues that we have. So the question, the really important thing is, as a society, how do we take advantage of the promise of these technologies, which is vast, but at the same time, reassure the public and make sure we ask the right questions to minimize the potential downsides of these things. But we must not forget the potential huge upsides. And I feel a little bit frustrated that much of the debate currently, in interviews and in the media, is focusing only on the negativity about AI. And it will happen. These technologies are coming, and we should be able to guide them to make sure that they are appropriate and use them. But we don't want to be certainly slaves of these technologies. But it's really important that the UK, and it has a positive viewpoint about them. Self-driving cars will happen, and I would love to see the UK actually making them, being, not just, part of some, ethical debate about, what these technologies. We should be creating these self-driving cars. We should be creating the new AI technologies, and we should also be involved in the AI debate, but we should certainly maintain our very strong, proud heritage in AI and manufacturing to actually continue to construct these technologies and not simply, only focus on the negativities and the potential downsides of technologies. We need to focus on the positive.
Yeah, but that's what media sells, right? Okay, I guess we are done because I know you have to go. Thank you so much, David, for everything.